Hello, friends. My name is Dr. Mark Hobson. I am a retired university dean, now a college professor, an ordained minister, and a writer of Christian books. I trust in God. I believe in neuroscience. I am also the father of Dr. Luke Hobson, the brilliant and kind educator from MIT. Today's presentation is a sharing of basic brain anatomy for adult learning with an emphasis on teaching and course design. I now share my screen, and let's begin this presentation. I learned this information while studying at Northeastern University. The field of mind, brain, and education is a collaboration of neuroanatomy, education, and the cognitive and developmental sciences. For this information, consider the mind as our psychological sense of self and our personality, located right up here in our prefrontal cortex. And consider the brain and nervous system as the controllers and coordinators of our mental and physical systems. Research from Johns Hopkins and other centers show that learners of all ages who know more about basic brain functions learn more and better than those who do not. Finally, I will make these slides available to anyone who wants them. My email is mark@drmarkhobson.com. We may have experienced courses where the instructor did not appreciate andragogy or how adults learn. Dr. Hardiman, Mariel Hardiman, is the researcher and designer of the 6 strategies of the brain targeted teaching model and the retired dean of education at Johns Hopkins University. Her research is instrumental in teaching and learning design excellence. She writes, all learning is brain based. All teaching, unfortunately, is not. Dr. Ernest L. Boyer was president of the Carnegie Foundation for the Advancement of Teaching. His quote of, "Learning begins with what the teacher knows," is our starting point, as I will share with you what I know based on the scholarship of great teachers who helped me learn. First, we will review the basics of brain anatomy and functions, and then review how this learning helps us teach and design courses. As I do not have a live brain to display because that would be illegal, at the close of this presentation, I will share a great resource called Brain Facts and display a 3D brain image that helps us learn. So let's review first these quick facts. The brain is the size of 2 fists put together or one grapefruit. It consists of about 78% fat and 8% of proteins. It has about 85 to 100 billion cells. Neurons are white cells, and neuroglia are gray cells or nerve glue that exists in the brain. Our brain uses 8 gallons of blood per hour and requires 64 ounces of water per day. Hence, the recommendation to drink 64 ounces of water every day to keep our brains healthy. The brain consists of 2.5% of the body's total weight, or about 3 pounds. It uses 20% of the body's energy, and it processes 10 to the 100 billionth power bits of data per second. We know the term dim bulb because our brain possesses 20 watts of electricity, or about the size of a refrigerator bulb. The hindbrain is the brain stem, the medulla, the oblongata, this area right in here. These areas control autonomic functions such as breathing and heart rate and blood circulation, as well as automatic and motor functions. Through evolution, these areas also now contribute to learning via movement and rehearsal. This area right here helps us learn by doing. The limbic system is above the brainstem and it regulates emotions. The limbic system is between the emotive and cognitive functions of our brain activity. These areas influence learning as events pass through short-term memory before moving into intellectual areas and long-term memory. In other words, all learning, before it becomes fixed, moves through our limbic system. The diencephalon includes the thalamus, hypothalamus, and certain thalamic nuclei. This area maintains homeostasis, or our body stability, allowing us to focus on information like in the classroom. The cerebrum is the largest section of the brain, with two hemispheres connected by a thick bundle of nerve fibers called the corpus callosum. The cerebrum is the largest part of the brain. It's responsible for conscious thought, sensory processing, voluntary movement, and higher cognitive functions. The cerebrum is where most long-term learning takes place in our lives. The brain's main functions are to keep us alive and to enable us to learn. 90% of adult learning comes through sight. To appreciate strategies of teaching and learning design, educators benefit from understanding our minds, how we learn, and how our brains expand during learning. We see the four lobes and the cerebellum, five key brain areas that process learning and memory. Think of an acronym, POTIF, that gives us a counterclockwise view of the lobes. The parietal lobe possesses sensory information from the opposite sides of the body. So the left side controls the right side of the body, and the right side controls the left side of the body. The parietal lobe processes sensory information like touch and other sensations. It helps position the body in space, measure the size of objects, grasp them, feel them, giving us our place in space. The occipital lobe processes visual information in conjunction with previously stored memories. The temporal lobe processes visual and auditory information, as well as spoken language. The frontal lobe, behind our forehead, is the thinking center for working memory, higher order problem solving, language, and speech. Regarding language and speech, there are two areas critical for learning and using language. The first is called Wernicke's area, a region of the brain that contains motor neurons involved in the comprehension of speech. This area was first described in 1874 by German neurologist Karl Wernicke. The Wernicke area encircles the auditory cortex on the lateral sulcus, the part of the brain where the temporal lobe and the parietal lobe meet. Broca's area is a region of the brain that contains neurons involved in many speech functions. Located in the front part of the frontal lobe and discovered in 1861 by French surgeon Paul Broca, who found that it serves a vital role in the generation of articulating speech. On this side, let's discuss feelings with feeling. The four major parts of the limbic system, the feeling area, are the thalamus, the hypothalamus, the hippocampus, and the amygdala. These connect the lower parts of the brain with the higher cerebral cortex functions like cognitive thought. The thalamus directs external information between our senses and our cerebral cortex. The hypothalamus relays internal information including appetite, homeostasis, or that fight or flight feeling. The hippocampus holds working memory and moves information to long-term memory in the cortex, also known as neuroplasticity. And the amygdala, also pronounced as the amygdala, is central to emotion. This evaluates information as a threat or a danger, and it relates it to the endocrine system, which is the emergency response center, and it also creates new cells called neurogenesis. Evolution provided a quick route for preparing an immediate emotional response. If the amygdala senses a threat, it triggers the hypothalamus, which activates hormones, increases blood pressure and heart rate, and triggers our muscle contractions. The emotional system then hijacks the learning signal. This type of anxiety and stress is quite real for learners, and enduring stress has a dulling effect on the intellect. For various reasons, many learners downshift or shut down their thinking, disconnecting their capacity for creativity and learning. Creating an emotionally safe climate enhances the development of 21st century skills, particularly creativity and imagination or spontaneity. Secure students learn and stressed learners struggle. As I mentioned, both hemispheres of our brains are involved in learning. The left hemisphere controls the right side of the body and supports words, language, calculation, logic, analysis, and detail. It creates a linear view of the past and the future. This area is part of the higher evolution of our learning. The right hemisphere is general concepts, sensory stimulation, pictures, intuition, creativity, spontaneity, the now. Both hemispheres are connected, and the notion of left brain and right brain personality or learning types is a neuro myth. It doesn't exist. We are feeling and thinking beings using both sides of our brains to process information, and we feel first before we learn. However, because evolution has made 90% of humans right-handed, left-handed people use both hemispheres of the brain more often due to motor behavior. Left-handed people tend to have greater creativity skills because they use more parts of their brains to process information. So you left-handers out there have some advantages and disadvantages when it comes to learning and retention. Overall, I wish I was a lefty. This slide is the building block of learning information and displays the structure of a typical neuron, the white cells of our brain. The brain learns through connections. When axons send signals that are received by these dendrites, learning takes place. When the brain learns, when the connection happens, it makes a popping sound and gives off a small spark. That's an aha moment in learning. Repeated practice reinforces these connections through myeliniation and changes the brain structure. The more connections are made, the signals move, they facilitate learning, and the brain is a muscle that wants to be efficient. New learning experiences stimulate nerve cells and create new pathways in the brain, leading to the growth of additional dendrites. Brain research and imaging show that a more enriched learning environment leads to a thicker cerebral cortex and increased neuroplasticity. We want to mix images, videos, pictures with words to create that thicker cerebral cortex environment. Neuroplasticity is the brain's ability to recognize its connections, while neurogenesis is the creation of new neurons. Much of this takes place in the limbic system, and together, neuroplasticity and neurogenesis enables learning, memory, and brain recovery throughout our lives. This slide talks about plasticity, learning, and memory. Neuroplasticity occurs when we learn new material. That's a process that learning design calls novelty. The brain evolves through learning. For example, a seminal study shows London cab drivers have larger hippocampi than London bus drivers due to specialized learning of navigation, while bus drivers follow routes. When we think about learning and memory, there are three types of memory to consider. The first is short term memory that allows us to retain information for immediate use, like a simple Excel formula or a phone number, and we hold on to that for about 30 seconds. Consider the cab driver remembering an address. Working memory is temporary, but enables us to perform executive functions such as planning, organizing, and rehearsing. The average capacity of this brain chunking method is 7 to 9 items. Remembering a phone number, for example, with more than 9 digits is difficult for most people. Consider the cab driver recalling different streets on an entire city block. That's working memory. Long term memory, if the brain perceives that learning, for example, a trial balance listing of ledger accounts for all debits and credits, or the capital city of all 50 states is worth retaining for us, this information may be moved from working memory to long term memory storage through a process called long term potentiation, or LTP, is the gold standard of teaching and learning design. For example, when I was about 7 years old, I learned all 50 state capitals from a puzzle map. I did it over and over again until I memorized all 50 names. I even won a prize on local television. So consider, in this case, the cab driver remembering a complete route to a downtown building. We want to teach and design courses that include these three types of memory in our learning design. This slide gives a quick overview of how to reach the three areas of memory in teaching and learning design. These lessons that I show up here are from a doctoral in education program for educators. First, they analyze a short-term memory exercise. Next, they add more difficult material and a chunking and scaffolding format with visual supports that build up to an assessment. And finally, they create a sequence that leads to real life or scenario based learning that the instructor and learner can actually use. Adult learners want to know what's in it for me. Theory work is great, but it needs a practical application for long term memory to take place for adult learners. In summary, as instructors and designers, we want to ask regarding short term memory: can I get the learner's attention? For working memory, can learners make sense of the information without becoming overwhelmed? And for long term memory, will learners remember and be able to use this 6 months from now? I close this video with material summarized from the work of Dr. Quanah Parker McGowan from Northeastern University in her course titled Learning and the Brain: Research into Practice. First, she says, we need to rethink the way we view students or learners. Research shows how to view learners in terms of their individual strengths and to tailor teaching strategies and design of courses to meet their needs. Neuroscience's contribution to understanding how to enhance long-term memory provides insights that can help educators develop strategies that play to a learner's strengths. Emphasizing the importance of emotion and learning. Emotional experience shapes the brain tremendously. Focusing on creating a positive and stimulating learning environment for learners enhances learning and helps students retain new material. We must design methods that are bright, cheerful, and easy to follow. This enhances learning and decreases stress. Adult learners are most stressed by poorly written directions, according to national surveys. Number three, challenging us how to expand our methods. Brain development data provides instructors with insights how adults learn best. We want to create a curriculum that reaches a diverse range of people. We know that one approach doesn't work for all learners, and we need to broaden our methods to connect with different kinds of learners. Adults want agency. We may want to give them a choice of topics to study that relate to the course's big picture, but also relates to their work or their learning. Number four, seeing how learning experiences impact the brain. Neuroplasticity has vast educational implications, teaching brains. From learning a new language to making connections across subjects, the brain responds to and adapts to new experiences. Neuroscience sheds light on when and how to create these experiences or novelty and make the most of students' windows of opportunity or interleaving. In other words, interleaving particularly helps connect what I already know to new information. Providing new kinds of feedback, number five. Applying neuroscience in the classroom helps instructors hone their ability to engage students, a result of using the four insights above. Faster and good-natured feedback that tells learners what they did well, what they need to improve, and how they can improve is an excellent feedback technique. This result is more meaningful and results in long-term, lasting learning. Again, research shows that learners of all ages who know more about brain anatomy learn more and better than those who do not. And finally, we close this presentation with a quick review of how this 3D tool may help us understand basic brain anatomy. We will review the brain hemispheres, the occipital lobe, and the hippocampus. I will be back with another edition of the Neuroscience of Adult Learning soon. And please write to me at mark@drmarkhobson.com, for questions or comments. I'm going to stop this display and I'm going to go to our 3D brain. I absolutely love this website and it is free, although I make donations to it. It's a nonprofit. So first, we see the brain and we can move our cursor over any part of the brain and it will tell us what we're seeing and explain it in more detail. Next, let's look at the right cerebral hemisphere. And we get an explanation for what happens in the right cerebral hemisphere, like there's 16 billion neurons here. Next, in the left cerebral hemisphere, we get an idea of how the cerebral cortex is divided into these two nearly symmetric hemispheres, and they're joined together by something called the corpus callosum that I mentioned earlier. Each hemisphere contains the four lobes that carry out specific functions, but some functions are shared by redundant areas in both hemispheres, while other functions are focused in a single hemisphere. Next, we'll take a look at the occipital lobe. I mentioned earlier that 90% of all learning comes through sight. And sight is what helps us to learn long term. So if we dial in to the occipital lobe and look at some of its functions, we can appreciate and use more information that are visuals to help our learners remember more. And then finally, let's take a look at the limbic system. All learning information from our senses passes through the limbic system before it goes into the lobes. And in particular, the hippocampus, which is a Greek name for seahorse, is an area that's responsible for long-term memory. If we create a positive environment for learners, they will remember it in their hippocampus and in long-term memory. So the takeaway for today is to make sure that all of our teaching and our design creates a positive, welcoming, emotional experience for our learners. That's it for today. I'll be back again with more.